course is too easy, or
The room change.
sorry?
The room change.
For this course.
Usually do.
This course, always thought so. Let's give it one more minute. Are there any questions about? No questions? So there is one last assignment for the course, which is due next week, the end of next week, and it was posted in Moodle. I think you've seen it. It is also in the course that the photocopy machine in the department is still broken, so there are some new lecture notes today, but they're also being posted in Moodle. I like to bring lecture notes when I can, but there is major fault. So the technician are in the room. I've been in the room for more than 2 hours. You know what they are doing. So any questions? Okay, so I guess. So we met a long time ago, so 5 weeks ago. I remember what I described in those 2 lectures. So yes, that's quite nice. So I gave 2 lectures in the course. The first was on linear algebra, kind of recap, and in particular singular value decomposition, spent quite a bit of time on that. And then I described the squares, I think, which you also have seen in supervised learning, and perhaps I guess that's the only course. And then we stopped there. So these were the 2 lectures. And so one idea was that you see linear algebra play an important role in these machine learning and statistical methods. So today we will see principal components analysis, and then we will discuss a little bit of spectral clustering. And so please pay attention. Okay. So I think principal component analysis you have seen in supervised learning, and perhaps at a faster speed, how we will see today. So, but let me know if this is slow. Sometimes I don't slow. So, right. So that's very important. Perhaps it's the most important method. I guess of a supervised learning method, together with k-means clustering, perhaps are the most widely known and used methods. So the idea is to you have data points, x1 for xn, and you want to find a new representation of these points, right? Which is a parsimonious representation. So the data points are in dimension, but you want to find a lower dimensional representation of these points. That's the idea. And so this is important for visualization. So for example, if the points are in high dimensional space, but you only want to represent them with 2 numbers, then you can represent them in the plane and you can visualize like where the points are in relation to each other. It is also useful for cluster analysis, because if you project down the point to a low-dimensional subspace, maybe you see that there are some clusters. So you visually see that the points are grouped into different clusters, right? And also it can be useful as a preprocessing. So maybe you want to do some supervised learning, so you also have labels, and you want to use this representation as an intermediate step for finding a classifier. Right? The classifier will be trained on the new representation. So the idea of PCA is, so first of all, it's a linear representation of the data. So what we will do, we will replace the points by linear transformation. So the goal is to find the linear transformation of the points. It will be a matrix, special matrix. And the way to do that is to say that this new representation is low-dimensional, but that it's not a random low-dimensional representation. It's one which captures most of the variance in the data. So that's the idea. So we need to understand how to describe variance of a set of vectors, right? And then we try to find the representation such that the variance in the new space, transform space, is maximized. That's it. So we'll see how to make this. So we will formulate an optimization problem, right? Where our goal will be to find this transformation matrix P, right, which is a projection. So remember what a projection is, or you want me to quickly review it? So it's a particular matrix which has symmetric, so it was an orthogonal projection, and has eigenvalue which are either 0 or 1. Okay. And so we look for a transformation P, which is a projection, which maximizes the variance. And the variance I've written it like this. Okay? So I made some assumptions here. So I've assumed that the points are centered, so they have 0 mean. Otherwise, I should have considered here also, right? So I should have written this as xi minus the mean, right? And this is the variance of a set of vectors, right? So normally the variance is referred to a set of numbers, but the same applies to the set of vectors, right? So it's right. So if you have second vectors, you say z1 to zn, right? And they are 0 mean. The variance is just the sum over I of zi norm squared, right? When zi's are scalars, this is just the standard notion of variance for a set of numbers. The same applies to a set of vectors. So the variance is the average distance of these vectors, assuming they have 0 mean. Otherwise, it's the average distance of this vector from mean. So here we want to find a transformation P such that these matrix P have some properties that we'll see, which imply that we have a k-dimensional representation of the data, and the variance of the transformed data is as large as possible. Okay, so that's the idea of principal component analysis. So the constraints are as follows. So we require P is a determinate matrix. It's a projection, so P squared is equal to P. Remember, this is the one property of projections. It's symmetric, right? And then we require that the rank is equal to K. So this means that the projection is k-dimensional. Okay. So we would like to solve this problem, and the solution of this problem we see is typically unique. And once we find it, we have a new set of points, which, as we will see, require smaller numbers, k coefficients, each of them to be represented, okay? As opposed to the initial point, which require d, written d is the dimension of the points. Okay. it's important that we get the notation and the probably statement right, so that then you can follow what remains in the note. So ask question if it's not clear. Okay. So now we are going to modify a little bit the problem and write more explicitly the projection as, if you remember, right, in this way. Because remember, orthogonal projection can be written as a matrix Q times the matrix Q transpose, where Q is a matrix which has orthonormal columns. So that's a way to represent projections. And this stuff is covered in the at the end of the first lecture notes. Right. So we write the matrix Q as little k columns, right? And these column vectors are orthonormal, right? So Q transpose Q is equal to the identity, right? And Q transpose is a projection matrix, okay? And as you remember, these vectors form a basis for a subspace, which here I call S, right? It's a k-dimensional subspace of Rd, and it is the space where we project to. Okay. So here we will take these points, right, which are right everywhere in the plane, right? These are the points xi. And we look for, say, one-dimensional projection, which retains most of the variance. In this case, if we go along this direction, right, so if P is equal to Q transpose is a one-dimensional projection, but clearly it makes more sense to project along this line than, say, along this line, right? Because to project along this line, you have larger variance of the projected points. So that's the whole idea, right? However, we don't want our projection to be one-dimensional, so we want to understand how to compute it in the general case, in which the dimension will be between 1 and d, these are dimensional points. So we can rewrite the problem in this this different form, in which we see that we need to find this matrix Q. Okay. So this is the variance. Okay, I just replace P by Q transpose, and then Q transpose the projection, and then the remaining constraint is that the Q transpose Q must be equal to the vector matrix. So this is the problem that we need to solve. Is it clear for everybody what this means? So if we solve this problem and we compute Q transpose X, this is a k-dimensional vector, which will be our new set of coefficients, our new vector of lower dimension, which replaces X. Right. Since we maximize the variance, we retain most of the information in the data. Right? So if K is equal to D, we can choose Q equal to the identity matrix, and we don't modify the data, so the variance is the largest possible. Right? If K decreases, it's clear that we will decrease the variance. Right? And we want to decrease it the least possible. That's why we maximize here over Q. Okay. So in other words, we can give a name to this maximum. So we call it. We could call it, say, mean of K, right? So what will happen is that μ1 is less or equal than μ2, and so on, right? Less or equal than μd, which is equal to the variance of the data. Okay. As we go down with our with the dimensions in the representation, we want to retain as much as possible the variance of the data. We will always lose something, right? We want to lose as least possible. So, yeah. So let's start with the case. So if we have a one-dimensional representation, so one-dimensional projection, the problem is easy, right? And it is equivalent to an eigenvalue problem. So how do you see that? Okay, so the matrix Q is just one column, right? And so the projection is Q transpose. And then we can do some little algebra, right? We can expand these so this square norm, what it is this vector transpose by itself. So it is xi transpose, and then is QQ transpose is QQ transpose because it's symmetric, and then you have QQ transpose xi. Right? So I have explicitly written this norm. Right? I have written it as this vector transpose by itself. Right? And now here you have Q transpose Q, which is equal to 1, because that's norm 1. Right? So this thing you can remove. Right? So this is equal to, right? So it's equal to, and the first guy you can also write as Q transpose xi because the inner product is symmetric. So this is equal to Q transpose xi squared. Right? So what I've written here. Right? So I'm doing all the steps. And but this also you can write as so Q transpose xi transpose Q, right? And you can bring the sum over I inside here. Okay? So when you bring the sum inside there, you get the empirical covariance of the data. Remember that the data have zero mean, right? So that it is exactly the empirical covariance of the data. Okay, so the objective function which I want to maximize for a one-dimensional projection, it is exactly equal to a quadratic form, right, which involves my variable Q, which I want to find, and the covariance matrix of the data. So we have succeed in rewriting our problem in a more familiar way. Right? So, I mean, I think you are more familiar with quadratic forms than with something like this. Does it make sense? Or do you want me to go for it one more time? So it's important to understand this also because if you understand up to here, I think you are more than halfway through to get the rest, which is a bit more technical. So it's important to get this part clear in your head. So we're not in a hurry this time. So just ask me if okay, so then in this case the problem is it's solved, right? Because we want to maximize this quadratic form, and the constraint in this case is just that Q is a vector of norm 1, and we know what the solution is in this case, right? So what is the solution? So it is a vector Q which maximizes this function, subject to the constraint that Q transpose Q is equal to Which one?
C.
Sorry?
The C vector?
The leading.
C?
C. Yeah, sure, yeah. So you need to look at the eigenvector of C. Now you need to look for the eigenvector with the largest eigenvector of C. That's exactly the definition of leading eigenvector is the one which maximizes this quadratic form. So another way to see that you need to. Well, this is a fact. Don't prove it, right? I think it's a part of our background, right? So maximizing this function with the constraint that q transpose q is equal to 1 is the same as maximizing this quotient, right? And you know that this is maximized when you choose little q to be an eigenvector of C and the eigenvector with the largest eigenvalue. Okay? So we see that if we have one-dimensional projection, right, which we represent, right, as Q transpose, so we transform our data with this one-dimensional projection, right, which means that we replace each point by just one number, which is Q transpose X. And this is the one-dimensional transformation. This is a one-dimensional representation which retain most of the variance of the data. Among all linear transformations. As I said at the beginning, here we transform the data linearly. So, this is good, but we want to understand the general case because often if we just do a one-dimensional representation of the data, the variance is too small compared to the variance of the original data. So you lose too much information, right? So if you take a set of images, say faces, you just represent it by one number each, then you cannot understand from this number what it is an image, right? So you need to choose scale that will be larger than 1, 10, 20. So then we need to understand how to solve this problem in general. So this is the main goal of the lecture, because this year you've seen already in other courses, but those of you who take supervised learning, but perhaps, I don't know, you tell me you haven't seen in detail why it is what it is. So it is not difficult, so that's why if you understand up to now, you are already halfway through, more than halfway through. That's why please interrupt me if something's not clear. Okay? So the idea is to repeat again the same tricks, but now we need to do it with the matrix Q. Okay? Well, first of all, I did something here, which I didn't do before, I think. So the variance of the data is 1 over n, sum over I. It is my projection, Q transpose xi squared, right? But I can remove the matrix Q, right? Because Q transpose Q is equal to the identity, so it's the norm of this vector is the same as the norm of this vector. Right? So I can remove the first matrix Q. So the objective function is a bit simpler. Is that clear?
Could you repeat why Q transpose Q times X is the same?
No, it is not the same.
But the norm
yeah,
is the same.
The norm is the same, right? And one way to see it, right, is that when you take the inner product of this vector with itself, in the middle you get Q transpose Q, which is equal to the identity. So you get xi transpose Q transpose. Right? I've taken the transpose of this vector times itself. So you have Q transpose xi. And this is equal to the identity. The dimension goes away. Right? So then you have this. Right? Now, so starting from this, we write the objective function as before, as a sum of quadratic bilinear functions in this case. Oh, sorry, quadratic functions. So it is the same procedure, right? So is this step clear? You want me to expand it? So you are neutral. I should skip it. So you do the same trick as before, right? So Q transpose X I squared, you write it this way. And then you interchange the sum as before, right? And you get the variance, the covariance, and then you have to get the sum of these column vectors of matrix Q of these quadratic function each of the vectors, right? Okay. So you just need to be able to expand these and obtain these and change the sum. Now, the problem now is a bit more difficult to solve. Because now our goal is to maximize the variance. So this is the variance in the k-dimensional projection. But we have more complicated constraints, which are that the matrix Q is has orthonormal columns. So the constraints are that the Qj have norm 1, and the inner product between any two of them is 0. Right? So it's a rich set of constraints which are making the problem more complicated. Right? In the absence of this constraint, I will choose all the Qj equal to the leading eigenvector, but it would be naive k-dimensional representation, because even though pretty naive, right? Because I replace all the components are the same, doesn't make any sense. So I want to each component of the representation should have a different meaning. So the question is the solution of this problem, you know what it is obtained by taking choosing Q1 to Qk to be the k leading eigenvectors of the matrix C. Right? And if these are not degenerate, they are unique. So there is a unique solution, otherwise you can combine them in some way. But so why is that the solution? So this was what we want to understand. Right, so okay, it's not difficult to understand that, but let's start from the diagonal case. So I want to argue that this k-dimensional projection is obtained by taking the k leading eigenvectors of the covariance. So let's start to understand why that is the case when the covariance is, the empirical covariance is diagonal. Right? So this corresponds to say that the data are uncorrelated, right? So this is like to say that the points are either on one axis or on the other, something like that. So we have some points here and some points here, something like that. So it's really a pathological case, right? So in that case, the covariance matrix is diagonal, and then here, so that's so our objective function simplifies to this one, right? Because so use the fact that C is equal to, so I write this as J, I write this as someone L,
can't actually see the.
Oh yes, that's called P. So use the fact that the covariance element LP is equal to delta LP delta L, and then you get this term. Right? It is equal to sum over L UJL squared. Okay. Is it correct? Yeah. So, and also I interchange these two sums. So when the covariance is diagonal, I can rewrite my objective function, which measures the variance of the projected data, as the sum, right, of the variance of each coordinate times this term, right, which is the sum over the different orthonormal vectors, L components squared. But now what we want to show in this case is that the maximum is attained. So we assume that lambda 1 is greater or equal to lambda 2 and so on. So the first coordinate is the one which has the largest variance, then the second, and so on. So here in this case, what I want to show that the solution is Q1 equal to E1, Q2 equal to E2, and so on, right? So the standard basis, the first k elements, are the solution of the problem. And the way I argue that that is the solution is by showing that the objective function is never greater than something, right? So I give an upper bound objective function, and I show that this upper bound is tight for that choice of the vector in the matrix Q. Okay. So summarize. I've rewritten the variance of the projected data as a sum of quadratic forms, and in the special case of diagonal covariance, I have further rewritten that as this function here, which is which contains the variance of all the coordinates, and then times these positive numbers, which measure the norm square of the nth row of the matrix Q. Right? So that's another way to see it. We have the matrix Q, whose columns are orthonormal, right? And here, what this term here is the square norm of the nth row of this matrix Q, right? So, and here there is something important to realize to understand why the solution is what we know it is. So, it's important to realize that this term here, right, which I've rewritten here, are less or equal than 1. Okay. Now, why are they less or equal than 1? Well, I think this I need to try to write neatly because it's very important. So, yeah. So this matrix has orthonormal columns, so that the columns have norm equal to 1, or square norm equal to 1, right? But if I take the norm of the rows, that will never be bigger than 1, right? The reason is that if I complete this matrix to an orthogonal matrix, so a square matrix, which has orthonormal columns, then the rows will also be orthonormal, right? So in that case, the rows will have norm 1. But if I remove some of the columns, the rows will have a smaller norm. Right? So that's one way to argue that this constraint is correct. Okay. So this is the important thing to realize. Here, I try to maximize this function and this function can also be seen as a sum over L, lambda L, times a number which is between 0 and 1. Right? What is the other constraint induced by the fact that the matrix Q has orthonormal columns? Well, is that the sum over L and J, L from 1 to D, so the sum of the square element of the matrix is less or equal than K. Right? But it is equal to K. This should be equal. Right? This is easy. This just says that since each column has norm 1, the sum of the square of the norms is equal to K. So this is right. So clearly, as a result of this property, right? So if I take my objective function, right? Right. So you can also look at these numbers. I could call them AL, right? So first constraints say that AL is less or equal than 1, but it's also more or equal than 0 because it's a negative number. And the sum of the AL is equal to K. Right? Therefore, it's clear that this quantity is less or equal than the sum of the K largest eigenvalues of the covariance. Right? Because I will choose a 1 through AK equal to 1 and the other equal to 0. Right? So that's the way to have an upper bound. So my objective function can never be bigger than that with these constraints, right? And now, if you choose indeed the Q1 through Qk to be the standard basis, the first K element of the standard basis, right? So E1 is 1, 0, 0, 0, E2 is 0, 1, 0, 0, 0, and so on. And you put them here, you actually get this number, right? So this argument shows that that is a solution. Any questions? And that's it. So that's the way to do it. And now we'll see that in the general case it's just this. So I think this is the most important slide as far as the technical argument concerned. So, right. For the general case, you just make a change of variable. So in the general case, C is my covariance matrix is non-diagonal. I can do the eigenvalue decomposition, so it's V lambda V transpose. And you can rewrite the objective function, the variance, or the transform data in this way. And then you can just make a change of variable. So you can call, right? So this we want to maximize over the constraint that is that Q transpose Q is equal to IK, right? But V is an orthogonal matrix. Right? So V transpose is equal to V transpose V is equal to the L V. So V is D times D. Although some of the eigenvalues might be 0, right? But you can still write full matrix V of eigenvectors. So some eigenvector will have 0 eigenvalue. So you can make a change of variable. So rather than maximizing over Q, we maximize over this Q tilde, which is a V transpose Q. Right? So you can also write this as Q of V transpose Q. Here I've written component-wise. And now in this new variable, the problem is like the previous one, is the diagonal case. Right? So the problem in this new variable rewrite as a sum over j of qj tilde transpose lambda qj tilde, and we solve it as we've done before. Okay. So for this transform problem, right, the solution will be q1 tilde u1 and so on, and then you go back and you see that qj is equal to bj. So this concludes the argument that the k-dimensional representation, k-dimensional linear representation of the data, which retain most of the variance, is obtained by looking at the eigenvectors variance matrix, imperial variance matrix, and choosing the k-leading one. Questions? I want to discuss another interpretation of PCA, which is interesting. Right? So here we see that PCA is a way to maximize the variance, but there is a kind of alternative or complementary way to look at this problem as PCA as a linear transformation which minimizes the reconstruction error of data. This is interesting because it connects PCA also to these squares that we have seen, which are part of this lecture we have seen a few weeks ago. Okay, and also you also see the role of the single value composition. So here is here. So we use this observation. So it's all based on this observation. So you have a vector x, right? And then use the orthogonal decomposition. So QQ transpose is our projection that we have determined, the one which maximizes the variance, right? But the norm square of the vector can be written as the norm of the orthogonal, the complementary projected vector, plus square, plus the norm square of the projected vector. So this is like a Pythagorean theorem, right? So you have a vector x, and you can project it here, and then you can project it on the complementary space, which is this, and the sum of the square of these two segment is equal to the square length of the vector. Okay. This is x. Q1 transpose x, Q2 transpose x. Right? Q1 and Q2 are orthogonal. So, therefore, if I then sum this over I, over my points, right? The second term will be the variance. The first term will be something else, which we will now interpret. But it's clear that if I maximize the first term, I minimize the second term, vice versa. Right? So rather than formulating search for a k-dimensional representation of the data as variance maximization, we can formulate it as the minimization of something else, which we now interpret. Okay. And so what is the interpretation? Well, yeah, one interpretation is mathematical, is a bit more obscure perhaps, is that, so this is the complementary projection, right? And right? So here we look for a projection which minimizes the variance, right? Because this is a variance, still a variance, right? Because you know that this matrix can be written as some other Q times Q transpose. It's a projection matrix. But this is not what I want to do. So what I want to do is here, right? That this quantity, right? And we will minimize the sum of this quantity, can also be seen as the smallest error that you can obtain by representing the points as linear combination of the columns of Q, right? So if you minimize this function over this vector Wi, which is k-dimensional, right? Because Q has k columns. So matrix Q times the vector Wi will be the dimensional vector, and so this is the dimensional, but the Wi will be k-dimensional, right? So the Wi I interpret as some coefficients. Coefficients of the linear combination of the columns of Q, which if the vector the closest possible to the xi, right? Since Q has orthonormal columns, so this is a very simple least square problem, right? The solution is Wi equal to Q transpose xi, right? So you can see that this is true by using the least square formula. Okay. So, Q transpose xi is the least square solution for this problem. And, right? So, minimizing 2, what is 2? So, as we said before, we can minimize over Q, and then we have the variance over the complementary projection, right? But using this observation, we can rewrite it as all this term. We can rewrite it in this way. Okay. So by looking at this formula, you can see that principal components, so the columns of Q will be the principal components, provide a sequence of best linear approximation of the data. Right? So here you try to approximate the data as best as possible. And this is intuitive, because if you maximize the variance, right, it means that the new representation stays as close as possible to the data. So it's kind of intuitive. Yeah.
So the Wi, the function of Q, is that correct?
Yes.
So that if you're minimizing that over, you can't minimize over, you can't change W without changing Q. So why are you minimizing over Wi? I don't understand. You need to minimize over Q.
Yeah, because this is our initial formula. Right?
As in you can't change Wi without changing Q.
That's correct. That's correct. But it's not contradiction. So
Okay.
let's go to the next slide. That's fine. Yeah. So you look for a matrix Q such that when you use that matrix Q to approximate the data in the sense of least square approximation, right? On average, over the data, you have the smallest reconstruction error. That's the meaning of this. So perhaps it is clearer if well, it's just a summary. I think we can skip it. Yeah, so this is just a summary to say that Q is equal to Vk. Vk are the k leading eigenvectors of the covariance. Right. So if you put here Q equal to k, right, This is the matrix which on average gives the smallest reconstruction area. Square reconstruction area. As a last, I think we should stop. Do you want to do 2 more slides or stop now?